Hello, everyone, and welcome to another edition of Terabit Talks Live. I'm your host, Chris Sass, and it's an exciting episode today. We are going to talk about where AI is going, where the network and AI meet, that inflection point. And I've been looking forward to this episode all summer. But before I start there, I want to thank our sponsor, Nokia, for making this all possible. Without Nokia's support, we wouldn't be here today, and we wouldn't be able to bring you this agnostic view of what's happening in the network world. We hope you enjoyed the content, and I hope you enjoy where it goes. I'm fortunate to have two wonderful guests. I'm going to do something a little different this time. I have a friend of mine I've worked with a number of years, a guy named Clayton Wigger. He happens to work for Nokia and he works for one of the leads in their AI practice. And whereas I see maybe hundreds of data centers, he sees a global view of the world and what's happening. He works on a lot of the standards bodies and things like that. So he's a great person to drive this conversation. And the conversation is with Alan Weckel from the 650 Group. If you're in our space, you know who Alan is, you know his reports are really valuable. And I expect this to be a really insightful episode. But Clayton, just from selfish point of view, I've seen a lot of folks talking about 800, in fact, doing 800 gigabit, 1.6 terabits on the horizon. I'd love to start with a little bit of feeds and speeds and then go from there. So I'm going to turn the show over to you. I'll be back at the end, but maybe you could start there and feed my curiosity of where we're going.
Yeah, it's
Welcome,
incredible to
guys.
think that we're on the cusp of 800 gig, 1.6 terabit. These standards have been evolving for a long period of time. And if you're a data center builder, if you're an enterprise data center builder, if you're building for a hyperscaler, you know that there's really no end to the appetite for the speeds of Ethernet. Ethernet's been a wonderful success story, of course. The investment in the ecosystem in Ethernet has been really like no other. But when we're talking about building data centers for AI, networking for AI, and of course that drives the significant amount of investment today. We're really here talking about deploying 800 today per GPU. So we're talking about hundreds of thousands in some of these large installations that you see on social media and in the news, hundreds of thousands of 800 gig ports. And there is demand on the edge of that for 1.6 in the future. But what is interesting about that, we're just leaving the 400 era, or perhaps we're in it for a lot of builders. But the demand for 800 has proven to be a bit more durable than a lot of us expected. And Alan, I know you track this quite actively. And when we're looking at 800 gig, when we line up the technologies that underpin that, we start with SerDes speeds and we go into PCI and NIC cards and network interfaces. That 800 market appears to be a little bit bigger than we may have thought even 12 or 18 months ago.
Yeah, absolutely. It is bigger, and I'd say we can point to AI for the reason, but it's also showing up in DCI, traditional server access, etc. 800 gig is going to be about a $4 to $5 billion market this year. And be well north of $10 billion next year. So insatiable demand. And it's really being driven by that 100 gig or 112 gig SerDes technology, right? So the whole complex in the data center is moving to X by 50 gig to X by 100 gig. So a fairly significant physics technology insertion point. And then we get the speeds and feeds associated with that. And just to kind of give a data set, probably since I've been talking, call it like the last minute, we've done dozens of switches. Like that's how many switches are being deployed. So these volumes are absolutely insane. It's not a couple switches per day or per hour. It's literally dozens of switches per minute is what the demand is for 800 gig or for data center networking at this point.
Heard an interesting statistic last month at the supercomputing show over in Europe, and that's in 2024, there were 20 Ethernet ports per second deployed worldwide, and it just speaks to that ecosystem. I've been around long enough to remember when Ethernet ran over a coaxial cable. So when you look at the speeds that we're talking about now, it's unfathomable. When I talk to people and say, look, you're a premium home internet service is 1 gig. We're talking about 800 times that, times hundreds of thousands of connections in a data center. And it might be, you might think as a more traditional data center builder, someone who's doing more CPU than GPU, you might look at that and say, well, it doesn't really matter to me. But I think my experience has been over the past 3 decades that the investment in the higher end and the consumption that we're seeing now, which is so outsized compared to how it has been over the past many decades, that's going to be a benefit to people downstream, let's say, folks who are maybe still at 25 gig per server, they're maybe considering 100. But the reality is that these technologies, 200, 400, 800, now 1.6, you have a whole wave of folks who are making the investments in that from a purchase side. That means the R&D is much more robust. And I would think that that means that those technologies would sort of filter their way down into market segments that otherwise would be a little bit slower to come up. Are you seeing that in your numbers? I know you track both data center as well as enterprise. You have a number of different products, and you can kind of see where those bubbles are. Are you seeing any sort of difference in adoption based on the technologies at the high end?
Yeah, absolutely. I think you hit a good one there, right? When we talk about this being 100 gig per lane technology, the next speed for the enterprise and for the rest of the market is going to be 100 gig per server, right? And so everyone who's thinking about 100 gig per server are mainly driven by the fact that they have massive core counts on these x86 processors now, is going to benefit from that cloud technology. And we're seeing the same thing at 1.6T, how that 200 gig SerDes will federate into some of the other technologies, whether that's traditional compute and kind of, the broader interconnect market.
Yeah. Well, and in a traditional data center, of course, with CPU, you're talking about workloads which are very different from those in AI, right? In the case of a traditional data center, that's connectivity. It's generally IP connectivity, a lot of APIs, a lot of data movement across. And so there's, we've played this game for a long time with Ethernet IP networks around stat muxing. We're able to sort of aggregate traffic and understand our traffic flows and build capacity where we need it. Spine leaf designs, of course, being a converged way that we build. If you're perhaps a heavier operator, you're using something a little closer to a fat tree where you have bandwidth all the way up the stack. AI is very different. Of course, the investment we're seeing today and the reason we have these high speeds, 400, 800, 1.6, is because it's a single coherent compute cluster. We need to make all of these GPUs, accelerators, look like they're a single entity. We need those gigantic pools of memory to store these very large language models to be able to access and move data. On the training side, of course, we're doing a lot of the training pathology of traffic is very interesting. It's very sort of step function as everything communicates at once. So we have to throw a lot of bandwidth at it, a lot of high quality bandwidth, very low packet loss, zero packet loss is the idea. Traditional data centers can be a little more forgiving of that. But really that memory coherence and compute coherence is the key for AI. And it's pushing us in a number of different directions in how we build networks and understand networks. Of course, what we'll talk about is that there's different types of networks, and we'll get to some of them in a little bit that are a little more maybe speculative or newer. But we have in a traditional data center, of course, you have your spine leaf design. Front end network is what we call that in AI. The back end network is really where those heavy demands are. And there have been other technologies which have served in there. People know about InfiniBand, which is a technology used in supercomputing for a long period of time. But Ethernet is finding its way into the back end in a pretty significant way. And I think from what I read of your reports, we see that market as a market with some outsized growth compared to the front end.
Yeah, it's kind of crazy. There's kind of like those aha moments or like wow moments there. And in traditional compute, we had a robust data center switch market, right? It was always a respectable CAGR to it. And then AI was ultimately an incremental network. That was kind of like the aha. It's not cannibalistic, it's incremental, and it's 10x the bandwidth, right? And so you kind of do that math out, then ultimately that scale out network becomes a larger TAM than traditional data center switching, just because it's 10x the bandwidth. And then eventually you get that inflection point on more GPUs than CPUs in the future. And then when we start talking about scale up, that's like 100x the bandwidth of traditional compute. And that provides that cache coherency. So suddenly you go from one network to three. They're all going to converge towards Ethernet, and you get an incredible amount of bandwidth. I think we talked about that a little bit earlier when we were talking about, hey, now there's one port per GPU instead of, say, 1 or 2 ports per server.
Yeah, it's interesting, folks who are just coming into the networking world for artificial intelligence, and of course, I had the opportunity to really talk with a lot of folks in a lot of different market segments. They're sometimes surprised if they're taken aback by the fact that every single accelerator, every single GPU has its own network connection. And once you walk through why that's necessary, again, we're really extending the memory and the compute capability so that it looks like one monolithic pod of infrastructure. And really that speaks to the way AI is developed and the researchers that are doing a lot of good work there. They're using software frameworks. A lot of these folks are not they're not familiar with the underlying technologies there. They know they have a certain number of flops to work with, and their interest is in the data itself and how to move that around. So when you abstract that using either open source or some of the vendor provide frameworks, they want to see a big pool of compute, and in order to do that, we have to build these networks. And you bring up an interesting point, and I talked about my history in the space, and I'm again old enough to remember when Ethernet ate through some of the other LAN technologies. Some listeners may remember Token Ring and ATM to the desktop, although we don't talk about that in polite company. But Ethernet has a history of working its way down and taking the proprietary and really absorbing it, because again, the investment in the ecosystem is so crazy. The scale up network is interesting. So we talked about front end networks, which is really our IP network for access to the cluster. The back end network's the scale out network, which is how we connect all the GPUs together and they move data around. But the scale up network is an interesting topic, right? Because to date, it's largely been the domain of NVIDIA with the fantastic products that they produce, NVLink, and that's how they're able to connect the GPUs together and provide this coherency. But of course, we know in the industry, there's an interest to, again, disintermediate that, or to bring the Ethernet goodness to that. There's some technical differences between the two for sure. NVLink is a highly integrated product with NVIDIA stack, but Ethernet is starting to peek in and show its way in there. There's a proposal from Broadcom, something called Scale Up Ethernet. We talk about it in the Ultra Ethernet Consortium, how Ethernet will ultimately make its way down there, and it requires a little bit of differences in protocols and deployment. But clearly, I know you've recently started tracking that market and are pretty excited about the size of it.
Yeah, scale up is going to be a $20+ billion market, and then Ethernet becomes billions within that 20 billion. So again, an enormous and incremental TAM there. And I think you highlighted a couple things. When we talk about Ethernet, the standards bodies are doing a tremendous amount of work there in order to improve the technology. So it's one of those cases where the bleeding edge Ethernet will show up. It will be timed to ASICs because it is a little bit more complicated to insert Ethernet, right? You need the right ASIC at the right time, the right SerDes. But we're at that point now where pretty much all chip design for these custom ASICs at the hyperscaler is going to end up on Ethernet. So it's kind of an exciting time. We barely are done talking about scale out being excited, and now we got this scale up opportunity, and we're just kind of see that more so in the fall. I'd say stay tuned for some of those trade shows where we see some really exciting scale up announcements.
Well, there are some interesting things coming out. Fall is certainly an interesting time. We have Open Compute will be once again, I believe in October. Check me if I'm right there, October. And then of course we have other smaller events around that. I think that it leads to an interesting question. Well, actually we have a great question here from James. How do you see scale up Ethernet impacting the competitive landscape between Ethernet and proprietary interconnects like NVLink or InfiniBand? And it's a great question. I think ultimately builders are going to have to make the choice on the right technology for them. We talk about these AI systems really as a system. There's a perimeter around them because they want them to be highly performant, want them to have the best in class technology and capability. At the same time, I've been around long enough to know that the bean counters will come. That's the phrase that I use, right? Ultimately, we're going to have to start showing the economics of AI, whether you're a hyperscaler or an enterprise. We have to instrument that. We have to understand what our output is, what the ultimate value is to the business. And when that happens, Ethernet compares very favorably. So, to Alan's point, I think that there's a tremendous amount of work within the standards committees. You look at folks like Ultra Ethernet, who is interlocked with IEEE around, some very important things like frame formats, making sure we don't break the network as it sits today. But, Ethernet has this proven pattern. I'm just a couple years younger than the Ethernet standard, right? And so we have seen it over the past half decade really march its way down through there. And so I think from a value standpoint, from a pricing standpoint, if you're looking at the overall envelope of what you're spending for an AI data center, if you can recoup some costs in the network and the interconnect, then you're likely to go ahead and redeploy that into some of the compute infrastructure, which is where the value is created.
Yeah, there's a day two operations component here as well, right? If you think about it, you can't have a unique scale up and unique scale out network for 5 or 6 different accelerators, right? As we move into the future, you're not going to have one accelerator for all of your workloads, right? And so when you move towards Ethernet, that gives you that day two operational efficiency as well. And so Ethernet is not only like a day one TCO cost, like you mentioned, kind of like the bean counter motion or the accounting piece. In day two, right, Ethernet scale allows you to get a little bit more uniform best practices, allows you to have more humans that are trained in the technology. And so ultimately, Ethernet will win there as well because of that kind of ubiquitous knowledge base that it has.
Right. We live in a world today with obviously a dominant supplier of the AI compute technology, but the reality is that there are plenty of not only alternative GPU, not plenty, but there are some alternative GPUs, certainly a lot of accelerators that are developed in-house for some of the largest consumers. If you've tracked the industry, you know that there's some great work being done on some of these in-house accelerators, especially on the inference side. And so each one of those, I think you have to view it as Ethernet dominant or perhaps Ethernet exclusive, right? If you pair up these vertically integrated technologies, that's fantastic. It gives you a lot of value today, but in the fullness of time, we know AI is here to stay, and we know these accelerators will make their way to market and provide opportunities for builders and enterprises to have many alternatives at different price points, different value points, different capability points. And it just seems natural that Ethernet is going to be the common element there.
Yeah, I think one way to kind of frame that is back in the day when we just had traditional compute, right? We're called that 2 years ago, right? But back in those old days of doing things, all right, the x86 processor market, both Intel and AMD, was about 5 billion a quarter, so call it 20 billion a year, just using round numbers here, right? In about 2 years, we'll have at least 4 and maybe 5 GPU, XPU companies that are doing that same number in and of themselves. So it's like there's just a tremendous amount of volume in that space. I think people always look at NVIDIA versus everybody else, but the everybody else numbers are fairly significant, right? No one's going to complain about a $20 billion a year revenue number.
Yeah, and as we look to deploy AI really in every facet of our lives, every part of the network, you're talking about edge inference, very small models, which might be capable of running on a CPU or some sort of custom ASIC or some sort of neural processor. In the case of our mobile phones, we know that that's been a thing for the last 2 or 3 model years with phones. So we can't think about it exclusively in terms of these AI factories. That's where all the noise is right now because of the spend. Certainly that brings attention to it because of the investments that are being made. But ultimately, when you move out of the training motion, which is where they're developing and creating a lot of the great science and outcomes that are coming from these language models and other models really, they will get themselves, they'll sort of filter their way out into all parts of the network. We tend to look at it as, we've spent half a decade here building networks for people, for eyeballs, right? They're ultimately limited by the ability of humans to consume the content. That's the CPU era. Now we're moving into the machine network. We're building networks that are many times as large, orders of magnitude larger, and that human network will become the access network in some ways. The access network is no longer a radio or a fiber or something like that. The access network is the entirety of these networks we've built before. So if you think about that paradigm, we know that AI is going to make its way into every single one of those places. And Ethernet is so well proven, so operationally ingrained, to your point, that it seems fairly obvious. I think what I think of next is, all right, we've talked about SerDes a little bit and how that affects the cadence of the growth and the speeds, but we have to connect it with something, and that leads me to optics, right? Optics are always very interesting because we have challenges on the speed side and building the network, but when we connect those things, we have a lot of good stuff going on in the optics world. We talked about the size of the 800 gig market, but as you and I talked recently, we talked about parallelism, right? It's not just parallel SerDes, but now we're parallelizing the interfaces themselves. Maybe speak a little bit about what you're seeing in that market. It would be tempting to think that there's one plug for every NIC card, but in reality, we have to think about the construction of the network and how that grows inside the building first, and then we'll talk maybe a little bit about interconnection.
Yeah, so inside the building, right, you have that one connection to the NIC, and then you have that leaf spine or kind of end of row architecture. So you end up somewhere between 3 and 4 optics per GPU or per NIC, depending on your architecture. And that's just for the inside the building component there. So call it intra-data center or the building level fabric. So it's a significant uplift.
And with a building being very interesting, and we're building some very big buildings and campuses, the reality is that the demands and the use cases around AI mean we have to start to federate that capacity over increasingly longer distances of time. The sort of the frontier, or the possibilities frontier today is bounded by space and power. Certainly power probably being the most critical of those. You see announcements from a lot of the large research labs and hyperscalers around doing purchase agreements and locking down power from given sources in certain areas. But what we're seeing is an increasing demand on federating that capacity over a distributed manner. So not just across a campus, not just across, my son lives in Northern Virginia, and I have to drive through Data Center Alley to get to his apartment, and I see all of these data centers around here. That's one problem set. But the demand, really, if you look at public statements, is we want to connect places like where I am, Atlanta, with Chicago, right? We want to connect. If you listen to Bikash from Google, does a wonderful talk where he says the data center is the entirety of a continent. And I think that's driving a lot of demand for different types of optics. So you might think of inside the data center, 800 gig short reach, but really there's also coherent and a lot of the other optics that are needed to provide that capacity across longer distances.
Yeah, I think we can double click on a couple of those. So the way I kind of think about it is, one, these buildings are large, right? We're talking huge size buildings. Whenever you drive by a data center, I think everyone's like, yep, that's a data center, right? They're kind of bigger than warehouses. And so you think about that to get from one side of the data center to the other, or from building 1 to building 2 in the same campus, right? You're talking like a few kilometers, maybe 2, something like that, in order to get there. And then you might have run out of land, or the next municipality might have power just for, say, right down the road. So then there's a sweet spot around like a 20-kilometer distance, right? You're not really spanning multiple metros, but you're kind of like within the metro, building out that farm for land reasons or power reasons to tap that in. And then you get into those metro regions around DCI, right? That 100-kilometer distance where ZR is kind of taking off there to do those connections. And then you mentioned Atlanta to Chicago, right? A ZR plus. So if you look at 800 gig, right, the standards bodies have come up with all those different variants in order to support all of those different distances. And it becomes very successful because it allows the operator to worry a little bit less about location. Obviously, everyone's worried about location, right? Location's the key in real estate. But ultimately, if you have all those different flavors, you always have the right tool in your tool chest, and that makes the operator's life a lot easier.
Yeah, and it's a lot about data movement. In my experience, people might think, well, AI training and inference is kind of sensitive to latency, so why would I want to combine those two sites together? But if you think about the use cases, especially for some of the hyperscalers, if you're a social media company, you're probably going to be wanting to move a lot of photos and videos and all that generated data. You might want to cost optimize that based on power or based on time of day. And so you want to have the flexibility, just like we do in CPU clouds today. You want to have the ability to sort of squeeze the balloon and get the most out of the infrastructure that you've built. Good question here from Kennedy. Given the rapid evolution of AI workloads, how do you anticipate the optics roadmap aligning with the compute roadmap? Isn't there a risk of a bandwidth bottleneck? And I think, you and I spoke recently about the next generation of SerDes as we go from 112 to 224. Now we're getting into some real significant physics problems. If I look over the last 10, 15 years, you can line up NIC cards, you can line up merchant silicon, you can line up optics. And really, we were talking about an incremental parallelization, good science being done there. But now we're running into some significant physics challenges when we get to 224 on length of traces on a circuit board, right? That to start to resonate if they're too of the wrong size. These have always been challenges, but we find them pretty significantly. To talk about, the mismatch between the workloads and the bandwidth. Talk a little bit about different optics variations. So I know CPO has made its way in the news quite a bit, but there's other technologies like LPO. I know, the industry is sort of looking to how do we synthesize the optics package with as close as possible to the network processing in order to gain the best efficiencies, both in power as well as that parallelization.
Yeah, so you mentioned LPO, there's LRO as well, and those are just different ways to do optics where you have a different amount of DSP content in order to handle the signal, or you put some of the signal processing or transmission directly on the ASIC. You're seeing retimers as well. You mentioned those pesky short distances continue to get shorter. And so what the industry is doing, I'd say at this point in time, is fine-tuning optics and copper in order to continue doing the same architecture. So we're saying, pluggable modules, copper, just at the higher speed, and there's not really a risk of mismatch. And then when we do reach those kind of laws of physics, like they're in the next decade or so, then that's when CPO and some of these more exotic photonics technologies will kick in. And you see that both in terms of parallelization as well as the exotic technology kind of ensure that we don't get those bottlenecks. Nothing will be perfect, right? When we're talking 100x the bandwidth, and no industry can move that fast. But kind of like all these things that have been occurring and the hard work the industry's been doing, kind of you chip away 10% here, 10% here, 10% there. You can kind of continue to scale for the next several product cycles without any issue.
Yeah, and actually that's where the hard work is. It's tempting, if you build data center networks, it's tempting just to think about a pluggable being kind of a dumb device that you plug in and it's going to give you the reach and the speed that you want. But in reality, as Alan just said, there's components inside of that. There's DSPs, there's retimers. Every single one of those consumes some amount of power and has some amount of cost to build, right? Not just the actual cost to build it, but the cost in terms of the complexity of creating that entire module together. And so teasing out what those different pieces are, finding the right way to incorporate the capability on this side of the link or on that side of the link, whether that link is an optical fiber or whether it's inside the switch or routed element itself. That's where a lot of the R&D is happening in the industry right now, and trying to optimize where that is. Of course, like any vendor, Nokia, we are taking a look at market sizing and understanding where the right bets to be placed are. And I think it's still a fairly open question what the ultimate the right answer will be. There may be multiple right answers, which often there are in the Ethernet world. Got another question here from Jeff. With respect to distributed training, how have you seen optical interconnects? Actually, he says, how have y'all seen optical interconnects, which I love because I'm in Atlanta, evolving to support low latency, high throughput workload requirements across geo-distributed GPU clusters? Great question. So we covered the need for the bandwidth between the two sites, but latency is a key piece of AI. And we talk about retimers, we talk about all the different components, Mac chips that are inside of these switches. Every single one of those has a small influence on the ultimate performance of the network when it comes to latency and throughput. And so the consolidation of those, to the conversation we just had, the consolidation of those is critically important. We're seeing today that the investments certainly are highly around training. And Alan, I think if I'm right, in 24, 25, you're predicting about 80% of the spend goes to training versus inference. But I believe that changes as you get to 29. 29 is where you go out to, if I'm thinking of the report right, 2030, if you extrapolate a little bit, that balance changes quite a bit from sort of overwhelmingly training to inference, which is more latency, less bandwidth sensitive, training being sort of very bandwidth sensitive. Latency would be a concern across distances. Am I getting my numbers right? That's kind of the where the envelope is opening up?
Yep, absolutely. And then you also, I'd say, you get a repurposing of some of those training clusters become inference as well.
Yeah, and just I realize not all people are familiar with Alan's products. We use it very actively inside Nokia. It's we were joking about it before we got started. I call it P138, which is his number, but it's his Ethernet switch data center report, which we find invaluable. It helps us understand what the market is doing, where the market is going, and you incorporate a number of sort of segmentation by customer, segmentation by technology. It's a pretty fascinating thing when it comes out. I know we meet at least once a quarter to talk about it. And as we mentioned before, expecting some exciting updates to things like scale up Ethernet, which provide a whole nother view to that. So I think we're running out of time here. Chris, I'm going to pass it back to you to finish us up here.
Great. Well, I appreciate it. It's been a whirlwind of a conversation. Not only does it sound like ports are getting deployed extremely fast, this conversation went extremely quick for me as well. And it probably explains why I'm on planes all the time if we're delivering all those ports and all the optics to make that happen. Ellen, it's interesting. I heard this whole conversation, but one of the things that's coming up quite a bit when I talk to folks is agentic AI. And we talked about the foundation, the network. How is all this going to be affected by agentic AI? Or maybe Clayton and Alan, both you guys want to take a stab at answering this, because I'd love to hear your perspective.
Yeah, agentic AI is kind of the wave of AI we're in right now. I call it wave 3, and I think others do as well. And it's where not only we, the consumer, start using AI, but the enterprise starts using it, right? So you can imagine agents making your interface to most businesses more successful. And if we think about agentic AI, it's going to be the first technology wave where we spend north of $1 trillion just in data center IT, right? So multiple trillion when you add in the building and cooling and land, but $1 trillion in kind of the networking compute that we had on this conversation. And that's just over the next, call it 3 to 4 years. So a fairly significant wave. And right after that, like as these agents get smarter and start improving our lives or improving a business workflow, we're going to get the robotic and transportation AI wave, which will be the first time we can say we have a multi-trillion-dollar infrastructure spend to support that. So I'd say we're just getting started, but we're at the point in time now where we're measuring these AI builds in the trillions instead of the billions.
Yeah, I think for folks that why is agentic? It's a buzzword for sure. Why is it important? Well, it's again, the first couple ways of AI really were limited to those training and inference models with a large language model. We're all familiar with ChatGPT. I'll give a shout out to Perplexity. I use that quite a bit. When you use a tool like Perplexity or DeepSeek or others, you pick your favorite. Now it's going out to the web. It's searching on your behalf. It's using other tools that very soon, if not already, will start to incorporate interfaces into travel sites and your Salesforce dashboard and really any sort of corpus of data that's out there. And when you think about how that's happening, that's not all happening in the RDMA high-speed backend of a training or inference cluster. That's going out using IP to call these tools, and those interfaces that are open and the ecosystem around. I keep using that word, but it's true. You have open source builders, you have enterprise builders that are building these tools, which are agents, and they all are able to talk to each other in a workflow. So that leads to a tremendous amount of east-west traffic, north-south traffic. It explodes because these language models are starting to self-reflect and talk to themselves and talk to other language models to verify their output. All of that traffic is highly standardized. We know that it's IP, it's APIs. They're talking in standard communications mechanisms that we have developed over a long period of time. And so again, I think that just speaks to the excitement around Ethernet, both in the traditional networks today, as well as those scale-up networks. I think once you start to consolidate on a common model, a common operational format, then we can de-risk a lot of different components. Different builders can start to interface with one another and bring a lot of value, which is what we're all really looking to AI to do, right? If we put a lot of money into it and we know it's going to affect our lives, and for most folks that are outside of the technology domain, it's not quite apparent. But for those of us that spend time in it, we can see how it's going to make our lives better in a number of different ways.
So there is a question that is asked by Harley, and basically it seems a little counterintuitive to some of the conversation we've had so far. But basically, do you foresee AI native fabrics becoming influential, and is that going to inflect the M&A activity going forward? What's your opinion on that, Alan?
Yeah, I do think we're at the stage where the next networking products, or say the 1.6T and then the 3.2T generation, will be the first ones purpose built for AI, right? Everything to date, like 800 gig and 4, was built prior to AI becoming a thing. And so we will have AI native fabrics, and absolutely we're seeing M&A there. Again, if you think about this going from $1 billion market to $1 trillion market. All the companies that are in this space will see an M&A wave. So kind of exciting times. I think ultimately that will lead to better products. And I'd say at the end of the day, when we're at a multi-trillion-dollar market, we're going to have more and not less vendors, but that will kind of have a nice M&A activity to it.
Well, as we wind down, I just ask one final question of you, a pretty simple one. What has surprised you from the activity you've been monitoring, what you've seen in the last year or two? Are there any things that jump out as stand out that you didn't expect to happen in the way the market's developed?
Yeah, I'd say it's the speed of adoption, right? When we look at 800 gig right now and the amount of ports shipping or how quickly people are rotating to scale up, the time to market is just faster. Like some of these ASIC programs are going to have 3 ASICs in 2 years versus 1 ASIC every 2 years. So we're just getting a far more rapid innovation curve. And that allows people to test technology and kind of implement technology a little bit differently than the historical data center, which was rapid moving, but a little bit more methodical and predictable.
Well, awesome. I really appreciate that. The speed has been the highlight throughout this entire conversation that I've taken away. It's just incomprehensible, the speed of deployment and everything that's developing so rapidly. I want to thank you, Alan and Clayton, both for being a guest on Terabit Talks Live. It's been a pleasure. Thank you both. For our audience, if you still have questions remaining, you're watching the video, don't be afraid to DM any of us. We will answer your questions. We'll get you an answer. We'll figure out what's going on. Terabit Talk Live is continuing to go on. We'll have new shows. As the name implies, we do live. My next live event, I think it's in Chicago, beginning of October. So if you want to see us live and you happen to be in that market, reach out to me. I'll let you know where we're at. And if you have guest suggestions, you want to hear content, or we didn't go deep enough, or you had things that we should have asked Alan that you'd love to know about, send them in. We'll figure it out. Alan, Clayton, thank you very much. And bye for now.